Let me show you how to be a good Bayesian. Change your predictions after taking information in.
Well, you mentioned causal inference, and that is certainly a hot topic, one where I always feel I'm a little bit behind. I've been reading about it and written about it a little bit, but I still have a lot to learn. So it's it's an interesting topic.
Yeah. And the cool thing is that, honestly, when you're coming from the Bayesian framework, to me, that feels extremely natural. It's just a way of, some concepts are the same, but they're just named differently. So that's all you have to make the connection in your brain. And some of them are somewhat new, but if you've been doing generative modeling for a while, then just coming up with a directed acyclic graph for a model and just updating it from a generative perspective and doing counterfactual analysis, it's really, really natural to do it in the Bayesian workflow. So that's a really good, that really helps you. To me, you already have the foundations and you just have to, kind of add a bit of a toolbox to it, like, okay, so what's regression discontinuity design? What's interrupted time series? Things like that. But otherwise, what's difference in differences? Things like that. But these are kind of just techniques that you add on top of the foundations, but the concepts are pretty easy to pick up if you've been a Bayesian for a while. So yes, that's really the good news for people who are looking into that. It's not completely different from what you've been doing.
No, I think that's right. And in fact, I have a recommendation for people if they're coming from Bayes and getting into causal inference. Judea Pearl's book, The Book of Why, follows exactly the progression that you just described, because he starts with Bayesian nets and then says, well, no, actually, that's not quite sufficient. Now, for doing causal inference, we need the next steps. So that was his professional progression, and it makes, I think, a good logical progression for learning these topics.
Yeah, exactly. And well, funny enough, I've started rereading the Book of Why. I had read it like 2-3 years ago, and I'm reading it again because surely there are a lot of things that I didn't pick up at the time, didn't understand, and there are some stuff that are going to resonate with me more now that I have a bit more background, let's say, or some other people would say more wrinkles on my front head, but I don't know why they would say that. So, Alan, I'm already getting off topic, but yeah, I really love that. And the causal inference stuff has been fun. And I'm teaching that next Tuesday. First time I'm going to teach 3 hours of causal inference. That's going to be very fun. I can't wait for it. Like, especially the live questions are fun, like you try to study the topic under all angles you consider. And then a student will come up with a question that you're like, I did not think about that. Let me come back to you. So that's really the fun stuff.
As you say, I think every teacher has that experience that you really learn something when you teach it.
Oh, yeah. I mean, definitely. That's really one of the best ways for me to learn. Having a deadline, first, like I have to teach that stuff. And then, having a way of talking about the topic, whether that's teaching or presenting, is really one of the most efficient ways of learning, at least to me, because I don't have the personal discipline to just learn for the sake of learning. That doesn't really happen for me.
Yeah. Now, we might not be as off topic as you think, because I do have a little bit of causal inference in the new book.
Oh, yeah?
I've got a section that is about collider bias.
Oh.
And this is an example where if you go back and read the literature in epidemiology, there is so much confusion. There was the low birth weight paradox was one of the first examples, and then the obesity paradox and the twin paradox. And they're all baffling if you think of it in terms of regression or statistical association. And then once you draw the causal diagram and figure out that you have selected a sample based on a collider, the light bulb goes on and it's, oh, of course, now I get it. This is not a paradox at all. This is just another form of sampling bias.
Yeah, well, I think actually let's talk about that. You want to maybe talk about what's a collider for, I was going to say the students, for the listeners, and also then what does collider bias mean and how do you get around that?
Mm-hmm. Yeah, no, this was really interesting for me to learn about as I was writing the book. And the example that I started with is the low birth weight paradox. And this comes from the 1970s. It was a researcher in California who was studying low birth weight babies and the effect of maternal smoking. And he found out that if the mother of a newborn baby smoked, it is more likely to be low birth weight. And low birth weight babies have health effects, including higher mortality. But what he found is that if you zoom in and you just look at the low birth weight babies, you would find that the ones whose mother smoked had better health outcomes, including lower mortality. And this was a time, this was in the 70s, when people knew that cigarette smoking was bad for you, but it was still, public health campaigns were encouraging people to stop smoking, and especially mothers. And then this article came out that said that smoking appears to have some protective effect for low birth weight babies. That in the normal range of birth weight, it appears to be minimally harmful. And for low birth weight babies, it's good. And so he didn't quite recommend maternal smoking, but he almost did. And there was a lot of confusion. I think it wasn't until the 80s that somebody explained it in terms of causal inference. And then finally in the 90s, where someone was able to show using data that not only was this a mistake, but you could put the numbers on it and say, look, this is exactly what's going on. If you correct for the bias, you will find that, not surprisingly, smoking is bad across the board, even for low birth weight babies. So the explanation is that there's a collider, and a collider in a causal graph means that there are two arrows coming into the same box, meaning two potential causes for the same thing. So in this case, it's low birth weight. And here's what I think is the simplest explanation of the low birth weight paradox, which is there are two things that will cause a baby to be low birth weight. Either the mother smoked, or there's something else going on, like a birth defect. And of those two things, the maternal smoking is relatively benign. It's not good for you, but it's not quite as bad as the other effects. So you could imagine being a doctor. You've been called in to treat a patient. The baby is born at a low birth weight. And now you're worried. You're saying to yourself, this might be a birth defect. And then you find out that the mother smoked. You would be relieved because that explains the low birth weight and it decreases the probability that there's something else worse going on. So that's the effect. And again, it's caused because when they selected the sample, they selected low birth weight babies. So in that sense, they selected on a collider. That's where everything goes wrong.
Yeah. And it's like, I find that really interesting and fascinating because it comes down to a bias in the sample in a way here. But also so here, in a way, you don't have really any ways of doing the analysis without going back to the data collecting step. But also colliders are very tricky in the sense that you have that path, as you were saying. So like the collider is a common effect of two causes, and the two causes can be completely unrelated. But if you control, as often said, if you control for the collider, then it's going to open the path, and it's going to allow information to flow from, let's say, X to Y, and C is the collider. X is not related to Y in the causal graph. But if you control for C, then X is going to become related to Y. And that's really the tricky thing. And that's why we're telling people, do not just throw predictors at random in your models. When you're doing a linear regression, for instance, because if there is a collider in your graph, and very probably there is one at some point, if it's a complicated enough situation, then you're going to have spurious statistical correlations which are not causal, but you've created that by basically opening the collider path. So the good news is that the path is closed if you, naturally. So if you don't control for that, if you don't add that in your model, you're good. But if you start adding just predictors all over the place, you're very probably going to create collider biases like that.
Let me me show you how to be a good Bayesian. Change your predictions after taking information in.